Hello and welcome back. Every day is a lucky day when you're doing quantum mechanics, but today's particularly lucky for three reasons. The first is we'll do one of the most ubiquitous, general, powerful and most broadly applicable calculations in all of quantum physics. That's no exaggeration, the harmonic oscillator. And I'll emphasise why this is such a ubiquitous and far-reaching and broadly applicable calculation. So whether you're doing the quantum theory of superconductivity, or the quantum theory of an electron, or the quantum theory of gravitational waves from a quantum perspective, harmonic oscillator is relevant, and everything in between. Gaussian wave packet, you would have been disappointed in a previous class when I spoke rather vaguely of flying fuzzballs for localised wave packets travelling through space. You would have been disappointed because of the imprecision of the concept of a flying fuzzball. I promise that we'd get more precise about what we mean by a flying fuzzball in the mathematical physics sense of the term. We do that in section 19. Finally, we consider Gaussian scattering from a potential barrier. And so this is a time-dependent quantum phenomenon, that there's a great deal of interesting quantum physics that you just can't see when you do chalk on blackboards, right? Complicated, time-dependent quantum phenomena. Sure, you can write down a formula for it, but you stare at it and it tells you very little. To actually see a movie of a wave function, or more precisely probability density, scattering, evolving in time, a flying fuzzball, for example, banging into a brick wall, which is what section 20 is about, we can see some intrinsically time-dependent quantum phenomena. By the way, our technology is sufficiently advanced that we can actually see quantum systems evolving in real time. For example, chaotic clouds of quantum gas, known as the Bose-Einstein condensate, are being built here at Monash and internationally. So time-dependent quantum phenomena are very much at the forefront of modern knowledge. But at the bedrock of much modern knowledge in quantum physics is this harmonic oscillator. And I want to begin by talking about the generality of this. You've met the harmonic oscillator in the sense of a mass m on a spring, S. And from one perspective, that's a boring system. Okay, it's necessary, but also boring from one perspective. But to emphasise the ubiquity of the idea of the harmonic oscillator, here we have this idea of a particle at equilibrium. If you were to displace that particle from equilibrium, it would oscillate. If that displacement is small, it'll oscillate sinusoidally. This is the harmonic oscillator. But let's consider a different example. I have some crystal, some regular arrangement of atoms in 3D. I'll just draw it in 2D. Well, here's a particle at rest. This crystal's at absolute zero. Here's a particle at rest. If I displace it a small amount from equilibrium, then there's going to be a restoring force trying to pull it back, just like here. It'll come back and overshoot and oscillate. If this displacement is small, then you can get simple harmonic motion in the sense of sinusoidal evolution with time. If I have some hill, this is the height of the hill versus position x. Now, mgh is potential, gravitational potential, so let this be a graph of potential, v of x versus x. Then if I was to have a particle at this point here, this local minimum of potential, that particle would stay stationary, but if I was to displace it, it would undergo simple harmonic motion for small displacements. Now, whether this is a ball at rest on the end of a spring, or an atom at rest at any point in an ideal crystal at temperature T equals 0, or an atom of blackboard in the blackboard, or a piece of gold in a lump of gold, or an electron in some nanodot, same idea. The electron in the nanodot is confined by some potential, and it's going to oscillate if you displace it by a small amount from equilibrium. I just want to emphasise the great generality of the idea of a harmonic oscillator, small displacements from equilibrium leading to simple harmonic motion in a classical sense. If these are billiard balls, point particles, question what happens when you consider the quantum mechanical version of this, the quantum mechanical harmonic oscillator. That's the topic of this section. Got the wrong bit of paper. So, quantum mechanical simple harmonic oscillator. As always, we want to make our life simple. So when I do that graph of potential versus x in the bottom right of the top board, let's change the coordinate system. Let's change the coordinate system, v of x versus x, so that the local minimum, whatever crazy potential you have, the local minimum is going to be at the origin. And that potential could have any crazy form. You do a different physical system, you'll get a different potential as a function of position. And the squiggly blue line is intended to suggest this. But I want to talk about small displacements about equilibrium. Now, this is a local minimum. So I'm going to fit a parabola to this. It's going to be an upright parabola. If we think Taylor series, there'll be a Taylor series expansion for v of x. There'll be a constant, which is naught, because of my choice of coordinate system. I made x go through the origin, and since energies are only defined up to an additive constant, I also shifted this point to the origin. So the constant term disappears. There'll be a linear term, a constant times x, but it too disappears because this is a local minimum. And the only term that's left will be some constant times x squared. Now there'll be higher order terms in the Taylor series, a different constant times x cubed, plus a different constant times x to the fourth, and so on. But if the displacements are small, x is small, x squared is really small, x cubed is really, really small, x to the fourth, you get the idea? So we're going to cross these off if x is sufficiently small, and consider the potential to be quadratic, something times x squared. Now I'm going to call that constant proportionality in equation 104. I'm going to call that constant proportionality half k. The reason I do that is because we know that the associated force, which will vary with position, is going to be minus dv dx, and minus dv dx, the 2 comes down, cancels the half, and you get the restoring force associated with a simple harmonic oscillator in a classical sense. So this is a restoring force, which tries to bring the particle back to equilibrium if you displace it by a small amount. Again, this is all classical, but we want to make a transition from the classical mechanics theory of the harmonic oscillator to the corresponding quantum version, which is the topic of this section. Now, I'm going to begin with the time-dependent Schrödinger equation, so the time-independent Schrödinger equation in one dimension. Yep. So minus h bar squared on 2m. By the way, the reason I hesitated when I wrote the h bar was because in fourth year quantum, we actually set h bar to 1. So I was sitting there thinking, this should be a 1. No, it shouldn't. It needs to be a h bar. All right. If you want to ask me about this after class, please do so. It amounts to a different choice of units in which h bar is 1. All right. So I'm writing down the Schrödinger equation. If this was in 3D, I'd write grad squared. Since we're in 1D, I write d squared by dx squared. Then we add the potential. And the potential for small x's is a half kx squared. That acts on the wave function, psi. The spatial wave function, which is just a function of position. This is time-independent theory. And this will give you the energy times the wave function back again. Now, I look at that equation and I don't like it. I don't like it because there's too many numbers there. There's h bar, there's m, there's k, and there's e. It looks like there's 4 parameters there. Are there really 4 parameters there? I want to make my life as simple as possible. I want this thing to be as physically transparent as possible. I want it to be as mathematically transparent as possible. Can I make some change of variables which takes the 4, what looks like 4 free parameters in this equation, and makes it a smaller number as possible? The answer is yes, there is such a change of variables. Now I'm just going to write down what that change of variables is and show you, or ask you to show in an exercise, that this time-independent Schrödinger equation, which looks like it has 4 parameters, will mush down into a single parameter equation. But I want you to ask yourself, where did that change of variables come from? Physicists don't just think, yep, that's the change of variables that will work. They try something and they screw it up. They try it and they screw it up again. They do that 4 or 5 times and then they write down the answer, which is equations 106, the change of variables. Again, this is third year physics. Almost nothing is elementary plug and chug. To get equations 106, do it by trial and error. As an exercise for you, stare at that, ignore what I'm about to write when you're arguing after class, and see if by trial and error you can come up with a change of variables that reduces what looks like 4 free parameters into 1. So the first change of variables is lambda. Lambda is not the wavelength, right? Lambda is a scaled form of energy. It's proportional to energy, so lambda is a scaled form of energy, not the wavelength. Omega is the angular frequency, 2 pi times f, of the classical oscillator. And when you studied springs in earlier courses, you know that this equals k on m, the spring constant on m. Xi, the Greek letter xi, is a scaled form of distance. It's proportional to distance x with some constant proportionality alpha, and that constant proportionality alpha is the fourth root of mk over h bar squared. So this is the change of variables that I'm going to make to the time-independent Schrodinger equation for the simple harmonic oscillator. And what you get is 107. And this equation I'm much happier with. Here's the wave function. It's a function of distance x, but we're now working in terms of scale distance xi. We have a second derivative with respect to the scale distance. There's a parameter, lambda, this scaled form of energy. Again, I emphasize lambda is proportional to energy. There's a scale distance squared. There's a wave function, and that all equals naught. By the way, my size will get progressively more like just squiggles. This equation I like it because it has one free parameter. The mathematics is telling us that there's only one parameter that matters here, and that is lambda, because that's the only free parameter appearing here. And since lambda is proportional to energy, this is saying all that matters is energy. Excellent. Now I want to solve this differential equation. Now what I'm going to do for the next 10 minutes is not quantum mechanics, it's mathematics. It's mathematical techniques for solving differential equations. Now, if I get thrown a differential equation I haven't seen before, one of the first things I might do is stare at it really hard for a minute and see if the answer comes. If I stare at that really hard for a minute, no answer comes. So the next thing that I might do is to express the solution, psi of xi, as a power series, some constant a plus some constant b times xi squared plus some constant c, not the speed of light, times xi cubed and so on, and then throw that in, and I'll crank it through for 20 minutes and it'll blow up. And the reason it blows up is because polynomials blow up, right? We've got a potential. Remember, we have a potential v of x. I'm just giving context to what's going to happen. And that potential gets infinite. It's a quadratic. Sure, it's only valid for small x, but we made the approximation. There's a quadratic potential. It's going to get infinite. Whatever my wave function is, it had better decay to 0 at infinity. When we go to plus or minus infinity, the wave function, I mean, it might be some complicated beast in here, but it better decay to 0 at infinity. Otherwise, we'd have infinite energy. Yep. If it didn't decay to infinity, you'd have a ball on top of an infinite hill, you'd have infinite energy. Polynomials are very bad at decaying to infinity. You give me any finite order polynomial, 1 plus 2x squared plus 3x cubed, etc., plus 15x to the 10th, set x to infinity, and it's going to blow up. Polynomials don't decay uniformly to 0 when any finite order polynomial will not decay. And that's the essence of why, the physical reason why, or the mathematical reason why, this solution will never work. So you do that, and you learn about Taylor series expansions to solve DEs. That doesn't work here either. So we need to be fancier. We need to use what's called D'Alembert's method, which I'm going to do now. So let's do it. We stare at this. We've made these conclusions, and we want to consider what's called the asymptotic form. I want to ask the question, how does this equation behave? I mean, how do the solutions behave at infinity? I can say as a physicist they must decay to zero, but how does the mathematics tell me this? Let's do this now. As a precursor to asking how does a solution decay to zero at infinity, let's ask how the equation behaves at infinity. If x, okay, this is now scale distance psi. If psi is infinite, then this lambda becomes irrelevant. Lambda is essentially energy, energy is finite. If psi becomes arbitrarily large in magnitude, this lambda might as well not be here. So the asymptotic form of the equation, as the magnitude of the scale distance becomes infinite, you just chuck away the lambda. So we end up with the second derivative of psi with respect to scale distance. Lambda's been thrown away, and we get minus psi squared psi of psi, which I'll put on the right-hand side. So this is the equation we need to solve. And this is the form of the equation, the asymptotic form of the equation. You're used to functions asymptoting. Well, the equations can also asymptote. This is the asymptotic form of the differential equation. And this equation can be solved, and you'll do so in exercise 34. When you solve it, you'll get... Now this is the wave function, but for large psi, this is the asymptotic form of the wave function. I've written an equal sign in the notes, but let me use a better mathematical symbol, which is a squiggle. This means is asymptotically equal to, or tends towards. So we have psi to the p, and e to the minus psi squared on 2. Now there's another solution, which blows up at infinity. I don't want to know about that, because that's unphysical. So I'm going to chuck that away on physical grounds, because I want this, I demand that this wave function decay to infinity. So for finite p and arbitrarily large psi, this is the form that the function takes. This is how the wave function decays to infinity. Sure, this blows up with psi, but this decays with psi, and transcendental functions always beat finite order polynomials, or stated slightly differently, infinite order polynomials, which can decay nicely to infinity, always beat. Their decay always beats, except in exceptional circumstances. So the point is, this thing tends to naught when psi tends to infinity, as you can prove. All right. So this is going to motivate an ansatz, which is a convenient mathematical form that helps us solve the problem. What we're going to do is this, and this is equation 110. What we're going to do is let the solution have a particular form. I want it to decay to infinity according to this. And then I'm going to multiply by some finite order polynomial. So instead of saying let the solution be a polynomial, I'm instead saying let the solution be a polynomial times this exponential decay. Now this polynomial, whatever it is, for very large psi, must be this, because that's the asymptotic form of the wave function. However, when psi is not large, this polynomial could assume a different form to describe some complicated behaviour of the wave function for non-large psi. So all of this has motivated this expression. And again, when psi is very large, so let me be more precise. This H, by the way, stands for Hermite, after the mathematician Hermite. And by the way, if you're the first person to solve a differential equation and you stare at it and there's no solution, then you pull tricks like this, and then you write down the solution, and it'll be some infinite series, and then you name it after yourself, or someone else names it after you. Hermite was the first person recorded by history and remembered by history, more importantly, to do this, and hence these polynomials are called Hermite polynomials. So the Hermite polynomial will be a polynomial in psi, some constant, I don't know, h naught, plus another constant times psi squared, plus etc., all the way up to the pth constant times psi to the p. If psi is infinitely large, then every term except for the last one is irrelevant. Psi to the biggest power will always be the biggest number when psi is arbitrarily large. So when psi is arbitrarily large, this polynomial will essentially be a constant times psi to the p. This will essentially be a constant times psi to the p times the Gaussian decay, which is precisely this. But all these lower order terms modulate or deform the polynomial to give it the behaviour that will make sure that it solves not just the asymptotic form of the Schrödinger equation, but the full form for any psi. And again, I emphasise this is mathematics, beautiful mathematics, not physics. It's mathematics applied to physics. All right. So we have this form, this ansatz, and we're going to substitute it, equation 110, we're going to substitute it into 107. What are we doing here? We've got a chain of functions. I initially wanted to know the wave functions psi of x. I've now scaled x. Now the unknown is the Hermite polynomial h. If you know what the Hermite polynomial is, you can construct psi, because it's this. If you know what psi of psi is, you know what psi of x is, and you solve the equation. We're actually never going to write down the solution. We're just interested in the energies, the allowed energies. All right, put 110 into 107 and you'll get an equation. And that equation will be 111. And it's the differential equation obeyed by h of psi. Now, since psi is the dependent variable, let me just denote by double dashed second derivative with respect to psi. And again, I'm quite serious when I say that you have a differential equation that's not solved. Solve it using techniques such as this. And then call it a special function, give it someone's name. This is the Hermite differential equation, and the solutions are the Hermite polynomials. Again, our single parameter, the scalar energy, appears. Now, I want to separately seek even and odd solutions. I want to separately seek even and odd solutions. An even solution, if I have h of minus psi, that's the same as h of psi. That's an even function. We can have odd functions. So I want to separately seek even and odd solutions. And the reason I can do that is because arbitrary functions can be written as a sum of even and odd. So let's separately seek these even and odd solutions. We seem to be a bit, what's the word? Biased towards evens. Anyone talking about even and odd solutions would first develop the even solution first. Maybe next year I'll do the odd one first, because I like odd things. All right, we want the even solutions, and I will write these even solutions as polynomials. And instead of writing a constant times psi to the naught plus a constant times psi squared and so on, I'll write it as a Taylor series. The coefficients I'll call c subscript k, indexed by the integers k. And I just want to have even powers of psi, because this is an even solution, so I'll just have even powers of psi in the Taylor series. The constants, the integers k will go from naught to infinity. I need to be a bit careful here, because I was rabbiting on about h as being a finite order polynomial. If I make h an infinite order polynomial, I may well screw up the asymptotic behaviour. I've been very careful to make my solution in the pink boxed equation at the top. I've been very careful to make sure my solution decays properly at infinity. If I make this an infinite order Taylor series expansion, that property may be spoiled. Now the answer is going to be, don't have infinitely many terms in this series, but I'm going to put by hand infinitely many terms here, and then something's going to come and bite me and tell me, no, I shouldn't have done that. And those comments will become more specific as we work through. So we now take this Taylor series expansion of the Hermite polynomials. There's an implicit assumption here that they are finite, that they are sufficiently well behaved to be described by Taylor series. We shove this into the Hermite equation into 111. So take this and put it into 111. So our chains just become more complicated into 111, and what you'll get will be 114. So this. So that's again an exercise. When you do it, you get the following. And there's something in that box, which is 2k plus 1, 2k plus 1, the coefficient of the k plus 1th term. There's our single parameter lambda and the coefficient of the kth term. Again, our chain of being, we had the wave function as a function of x or as a function of psi. Then, and that's what we wanted. Then we could reduce the problem to working out the Hermite polynomial h. Now we've got a bunch of coefficients, c subscript k. So if we were to solve for the ck's, you could ask the question, how do you solve for the ck's? You know the ck's, hence you can construct the Hermite polynomials. Hence, having known the Hermite polynomials, you can put them into 110 and construct the wave function. Again, we just want the energy, but if you wanted to work out the wave function, this is the chain that you'd follow. So I have this expression here. Now, I'm going to argue that this thing in square brackets is naught. Now, I'm talking a bit too much, so I've got a question for you, which is, why can I say that this expression in brackets is naught? Let me ask a bizarre question. What's the Taylor series expansion of naught? Have a guess. So let's consider naught to be a function of x. What will be the Taylor series expansion of x? Something plus something times x plus something times x squared. Sorry? Zero coefficients. Beautiful. So 0 plus, okay, let naught be a function of psi. Naught plus naught times psi plus naught times psi squared plus naught times psi cubed, and so on. So the Taylor series and you can work this out with the Taylor series formula. You'll just get naughts, right? Every coefficient is naught. That's naught, and this is a Taylor series expansion of naught in even powers of psi. Every coefficient must be naught. That's one of two ways that you can directly argue that what's in square brackets is naught. A second way is to point out that the set of all powers of psi, so here's the set of all powers of psi, where k equals 0, 1, 2, 3, etc. So this is a set of functions. As you learned in linear algebra at level 2, if you have a linearly independent set, and a certain linear combination of elements of a linearly independent set vanishes, then every coefficient must be naught. The set of powers of psi, arbitrary powers or even powers, is a linearly independent set. This left-hand side is a linear combination of elements of a linearly independent set, and the fact that that vanishes implies that every coefficient must vanish. Irrespective of the logic that you use, either the Taylor series expansion of naught or the linear independence of even powers of psi, you learn that what's in square brackets must vanish. So what's in square brackets equals naught. And when you write down that equation, you can manipulate it by solving for ck plus 1. And what you get is the following. And this is called a recursion relation. This is called a recursion relation. Why? We've got a bunch of coefficients c that describe our Hermite polynomial. This bunch of coefficients. The first is c0, the next one is c1, the next one is c2, and so on. Suppose I was just to pick an arbitrary value for c0, a number, a non-zero number. Then this recursion relation would be like a frog. It would tell me how to get from c0 to c1. You tell me what c0 is, I put it into this recursion relation, equation 115, and I would work out what c1 is. If I knew what c1 is, make k equal to 1, I'd hence be able to work out C2. So pick a number, any number as long as it's non-zero, use the recursion relation to get all the coefficients. You would then have all the coefficients ck here, hence you would know what the Hermite polynomial is. Once you knew what the Hermite polynomial is, you could put it into equation 110 and work out what the wave function is, and sketch, for example, its probability density. We won't do that, because I just want to be more pragmatic and ask the question, what are the energies? So let's apply these recursion relations. By the way, you might be asking, pick a number, any number for C0, as long as it's non-zero. Isn't there some arbitrariness there? No, because the wave function that you ultimately construct must be normalised. The integral of its magnitude squared must be 1. That can be used to fix the magnitude of C0. Again, we won't go there, we just want energies. So we had this recursion relation, and we could, if we wanted to, divide through by ck. And this tells us that the ratio of subsequent coefficients in our expression for Hermite polynomials, the ratio of subsequent coefficients decays. How do I know that? Well, if I look at this formula and I make k huge, k is huge. Huge means much bigger than 1 and much bigger than lambda, so the numerator is 4k. I'm going to rub out that 4 soon. Huge means that k plus 1 is k. Huge k means 2k plus 1 is 2k. So this is 2k times 2. The 2 and the 2 cancel the 4. The k leaves a k squared, which cancels one of the k's. So this is telling us that as k becomes large, the ratio of subsequent coefficients vanishes, but it doesn't vanish fast enough. And as you show in exercise 37, the resulting wave function, work out the k's according to this formula, the resulting wave function diverges, and it diverges catastrophically. This is the bite that I mentioned earlier. This thing diverges, it tends towards psi to the 2p, which blows up for large psi, times e to the psi squared, which also blows up for large psi, and this makes us sad. And so this is a problem that we need to fix, right? How do we fix it? The answer is as follows. And we're 2 steps away from working out the quantized energy levels of the harmonic oscillator. That the origin of this blow-up was allowing this series to travel to infinity. But suppose there's some particular term, C subscript capital N, there's a particular value of k, that index k, let's call it capital N, there's a particular value at which this coefficient equals 0. If that particular coefficient equals 0, then a recursion relation with the ck on the right-hand side, our recursion relation implies that every subsequent coefficient is 0. Because this basically says ck plus 1 equals a number times ck. If ck is 0, then ck plus 1 will be 0, and every subsequent coefficient will be 0. So the series will terminate. That's good. This infinity that made me sad is no longer there. This becomes a finite order polynomial. The asymptotic behaviour of the wave function is not spoiled at infinity, which is good because we put the asymptotic wave function behaviour in by hand. So we're just going to demand that there's some number n at which the coefficient is 0. So we look at this and we say there's going to be some particular value of k. We don't want this blow up, it's unphysical. There's going to be some particular value of k, which we call capital N. And for that particular value of k, so it's actually the n plus 1th coefficient that vanishes. The next coefficient, ck plus 1, this will become a 0. We're demanding this be 0 for that particular value of k. And that truncates the series, keeps the asymptotic behaviour, and solves the problem of the divergence. All right, we have this equation here. So lambda is going to be equal to 4n plus 1. Now what is n? N will be 0, 1, 2, etc. But lambda was a scaled form of the energy. I was emphasising the fact that it's a scaled form of the energy because we use that factor now. E is lambda up to constant. So let's replace lambda with 2e on h bar omega. And when you then solve the resulting equation for E, these are the energy levels, the allowed energy levels for the simple harmonic oscillator, done the quantum mechanical way. And these are for the even solutions. Now, if you do the same procedure for the odd solutions, and I'll leave this as an exercise for you, what you get is a very similar looking formula. And these two things can be put together into one formula, which is the key result, and probably the most important equation in the course. Not the most used equation in our course, but the most important equation. And this is one of the most important results in theoretical physics, certainly in quantum physics. The energy levels of the simple harmonic oscillator are quantized. Give me an n, which is 0, 1, 2, 3, all the way up to infinity, and the energy levels of the simple harmonic oscillator will obey this formula. So what do those energy levels look like? Well, when n equals 0, you have the so-called ground state energy. When n equals 0, E0 is h bar omega. So the energy for n equals 0 is not 0. So when you have when you ask what is the minimum energy, that minimum energy is not 0. It's half h bar omega. When n equals 1, the first excited state will be 3 halves h bar omega, etc. And these energies go all the way to infinity, and they're all equally spaced by an amount of h bar omega. So this is the simple harmonic oscillator, and again, we've not solved one quantum problem here, we've solved infinitely many. Any problem that involves a single particle, which obeys a Schrödinger equation, exhibiting small oscillations about equilibrium, whether it's an electron in a nanodot, or an atom in a crystal and so on. These are the solutions for small oscillations, and again, this is very, very ubiquitous. These energy levels are quantized. That doesn't surprise us because this is quantum mechanics, but again I want to emphasize that in quantum mechanics not everything is quantized. Let's now look at the Gaussian wave packet. So here the context is a one-dimensional world, one space and one time dimension, so we're in 1 plus 1D. We're going to have a wave function. It depends on position x in our one-dimensional world and time. The Gaussian wave packet is a flying fuzzball. Too hard. It's a flying fuzzball in the sense of being an exact solution to the time-dependent Schrödinger equation in 1D. All right. Sometimes what's obvious to you is not obvious to me. All right. This is an exact solution to the 1 plus 1 dimensional Schrödinger equation, the time-dependent Schrödinger equation in one spatial dimension. So we have a constant. This constant ensures that the wave function is normalized in the sense that the integral over all space of its magnitude squared is 1. This is going to be a time-dependent amplitude. Now, delta p subscript x is, ultimately we're trying to describe a wave packet, so at some instant of time, its probability density, and I'll render this more precise soon, at some instant of time t, a particular time t, the probability density will be localized, and it's going to have the form of a Gaussian. This thing's actually going to move, by the way. Now, since this is localized, it's going to have some width, delta x, some uncertainty in position. But you know the Heisenberg uncertainty principle for position and momentum. that if there's a certain width to this flying fuzzball, this localized wave packet, as described by this probability density, then there'll be an associated uncertainty in the spread of momentum. Yep, so this is the spread of momentum, and since we're in the x component, in the x direction, I put an x subscript. That's the px that appears here. But what's in the square root is just a t-dependent function. And at this point, my eyes are already beginning to glaze over, because this is a big formula that's difficult to understand. And that's fine. In the tutorial, and to a lesser extent now, but in the tutorial, which is our next class, we'll go more into the physical meaning of being able to see the physical meaning behind these equations. So this square root term is dependent on t. Where does the position come in? It comes in this final part of the expression. And I've lost interest by now, right? There's x's, there's t's. I stare at it makes no physical sense. I'm not even going to write it down. But you need to switch off your physics brains for a second, take this expression, equation 122 in the notes, and show explicitly that it solves the time-dependent Schrodinger equation in one dimension x, one spatial dimension x. So that's a mathematical exercise, which I'll leave to you in exercise 39. So my eyes have glazed over, I've lost interest, but something that I'm not going to lose interest in is the probability density, and this is going to be the magnitude squared of the wave function. How would I calculate the magnitude squared of the wave function most efficiently here? If I ask you to calculate it, as I do in an exercise, the most efficient way to calculate this is to multiply psi by its complex conjugate, and then use every complex number trick you know. And when you do that, in exercise 40, you'll get equation 123. I'm not sure if there's enough room there. So this is the probability density, the spread of momenta, Planck's constant on 2 pi, a root pi. My eyes are glazing over again, but in the tutorial we'll work out the physical meaning of this. Delta px to the fourth, t squared, m squared, h bar squared. I'll just make the superficial comment now that when t is 0, this will be a maximum. As t gets bigger, this will reduce. This will correspond to a decaying of the peak of the Gaussian wave packet with time, a point that I'll pictorialise on the next board. Then we have negative, and then there's some number, and sorry I'm being lazy, this is just some number that depends on time. I'm going to call it psi. It's written in full in the notes. I'm not doing it to be lazy, I'm doing it because it makes it more physically transparent. This is a Gaussian, namely something of the form, for fixed t, it'll have the form of e to the minus something times x squared, that characteristic Gaussian shape. Where is it centred? It'll be centred where x equals vt. That's interesting. This reminds me of Ehrenfest's theorem. The peak moves to the right at a speed of v. If I consider 3 subsequent times, let's say t equals 0, t equals 1 second, t equals 2. When t equals 0, this is some number, which will be its maximum value, considered as a function of time, times e to the minus some number times x squared. E to the minus x squared is a Gaussian. So this is t equals 0 with the pink chalk. We let the wave function grow old. We let t equal 1. The peak has moved. In fact, the peak is moving to the right. Peak is moving to the right. Position of the peak, x equals vt. It's moving to the right at uniform speed. Ehrenfest's theorem says that expectation values should behave classically if your potential varies slowly enough. There's no potential here. You're in vacuum, there's no v. The centre of mass of the wave packet is going to be moving to the right at uniform speed. So if this is the centre of mass of the wave packet, the peak, at t equals 1, the peak will be at x equals v times t, where t is 1, at t equals 2, etc. The peak is moving to the right at uniform speed. It's behaving classically, a free particle, no forces, uniform speed. So we move to the right at time t equals 1. This amplitude has gone down, but this psi of t gets smaller with increasing t. So even though the peak of the Gaussian has decreased in height, the width of the Gaussian has increased. This has a name, by the way. It's called the spreading of the wave packet. The wave packet is spreading. By the way, the wave packet's normalised. The area under it must be 1. If the peak reduces, it must get wider. So this is the spreading of the wave packet associated with wave functions growing older. Notice by the way that the wave function is getting more delocalised. At t equals 2, the peak goes down again, and the wave packet becomes wider still. So decaying, like a Gaussian, but very wide. So we have the peak moving at uniform speed, as you'd expect from Ehrenfest's theorem. The peak moves classically. The area stays as 1, but the wave function spreads. All of this comes from equation 1, 2, 3, and more. And we'll investigate this solution much more thoroughly in our next class, which is a tutorial. The last thing I want to do today is one-dimensional potential scattering. What I've just drawn is interesting time-dependent quantum phenomena. We've studied, in this case, a flying fuzzball, the Gaussian wave packet, evolving through space. We've also studied the problem of a square well. Now, the opposite of a square well is a potential barrier. So I'm doing section 20 now, Gaussian scattering from a wave packet, Gaussian scattering from a potential well. Now, you can actually write down a formula. If you ask the question, if I have some potential barrier, so here's some potential barrier, and I ask the question, what happens if I take this potential barrier and fire a Gaussian wave packet at it? Now I'm going to have a series of frames, t equals 1, t equals 2, 3, etc., all the way up to 9. Now you can actually write down a formula for the question, if I have a Gaussian, some Gaussian, travelling to the right and hitting a potential wall, you can write down a formula for the wave function and the probability density. It's so horrible, I'm not even going to think about writing it down here or in the notes. You stare at it and it tells you nothing, but then you plot the probability density, which is what this is, as a function of time. So we have this static potential barrier, which appears in each frame, and we're going to ask the question, how does the probability density behave with time as the wave function grows older? Wave function grows older means solve the Schrodinger equation. So you've done that and you plot it. So what do you get? Good question. This is in figure 16. So the wave packet moves to the right and spreads a little bit. The area is always going to be the same. But as it starts to strike the upper end of the barrier, there starts to be some oscillations here. So these oscillations are interference between the incident wave packet and the packet that's beginning to be reflected from the barrier. When you get closer to the barrier, the wave function starts to bunch up and you start to get very violent oscillations. These violent oscillations are due to the interference, again, between the incident and scattered wave packets, giving these interference fringes, reminiscent of Young fringes. The whole packets become narrower, by the way. You chuck a tennis ball at a wall and it gets flatter. You chuck a wave packet at a potential barrier and it gets skinnier. Because its area must be 1, it gets higher. So these oscillations get progressively more violent and the thing becomes progressively thinner, but it starts to penetrate the barrier, which is what this is. All right, this process continues. We actually start to get a bit of a pulse that's inside the barrier and it's travelling on its way to the right. Now we start to see, and you can see movies of this on the internet, we start to see a reflected wave packet differentiating itself from the mass. There's still these fringes due to the fact that there's still some incident interfering with the reflected, but there's also a well-defined piece of wave function inside the barrier that's moving slowly to the right. In fact, this peak pulses back and forth, reducing in amplitude as it leaks out on both the left and the right. That's illustrated more clearly in the next slide. This is now the differentiated Gaussian wave packet, and it's a smaller hump travelling to the left. That's a reflected wave packet. We still have this peak going back and forth, but we start to have a transmitted wave packet leaking out. Wait a bit longer. The Gaussian on the left is going to the right. This peak in here is slowly decaying in amplitude, and we have a fairly broad wave packet on the right. We wait long enough still. The Gaussian on the left is way over to the left. It's getting broader and broader with time. There'll be a little bit trapped in here, which is called a resonance, but it's slowly leaking out into the tails of the reflected wave packet. And these time-dependent phenomena, again, these things can be built in the laboratory and imaged. Sorry for going over time. I'll see you in the tutorial. Thank you.